everyone, welcome to the second lecture of Chapter 2. Today we are going to talk a little bit about isotopes and see how those isotopes kind of allow us to calculate that average atomic mass, which is the atomic mass that you're seeing on the periodic table. And then we're also going to talk a little bit about how the periodic table is actually arranged and why that's really cool. So our first topic is isotopes. Isotopes are atoms of the same element that have different numbers of neutrons. So if you'll recall from last time, we talked about John Dalton's postulates about the atom, and one of those was that atoms of the same element will have the same mass, and that would be characteristic of that element. Well, that's not quite right. Atoms of the same element have the same number of protons, right? Remember last time we talked about the fact that protons identify which element it is. But atoms of the same element can have different numbers of neutrons. And when they have different numbers of neutrons, that causes them to have a different mass number. Because if you'll recall from last time, we said that our mass number is equal to the number of protons plus the number of neutrons. So if the number of neutrons is different, then it will have a different mass number. So atoms can have different masses because they have different numbers of neutrons, but they will always have the same number of protons for a given element. And carbon, for example, has 3 naturally occurring isotopes. So the number of protons here is always going to be 6 because that is how we know it's carbon. Anything that's carbon will always have 6 protons. Anything with 6 protons will always be carbon, right? That's how we figure out that it's carbon. The number of electrons is always going to be equal to the number of protons for a neutral element. So since this is neutral, if it has 6 protons, it's going to have 6 electrons. Now the thing that can be different, right, and that doesn't depend on anything is this number of neutrons. It can have as many or as few neutrons as it wants, really. So the most common isotope of carbon is carbon-12, and that has 6 protons. And this, you may not be familiar with this notation, this C, either carbon-12 or C12 here. That 12 is telling you the mass, okay? So these are different isotopes. This is one way of writing isotopic notation. You write the name, dash, and the mass. So like carbon-13, its mass number would be 13, and carbon-14 would have a mass number of 14. And so carbon-13 has 7 neutrons, right? So this is a different number of neutrons than carbon-12. And the way that we're getting that mass number, right, we're doing neutrons and our protons, that is giving us the mass. Same thing here, carbon-14, again, different numbers of neutrons, but 6 plus 8 gives us 14 there, okay? So different isotopes will have different numbers of neutrons. They'll all still have the same number of protons and electrons, though. So the atomic mass on the periodic table is an average of all of the elements' isotopes. But it's not just, like this last one, right? For carbon, we don't just add up all the masses and divide by 3. It's not a regular average. Instead, it's what's called a weighted average, okay? And the weighted average part is it's going to be based on the percent abundance. Not all of these isotopes occur at the same frequency in nature. Some of them are more rare than others. Like carbon-12 is super duper common. Most carbon is carbon-12, whereas carbon-14 is really, really rare. It has a low percent abundance. So the mass on the periodic table of carbon is 12.011, and that is an average mass. So it's telling you most of the carbon is carbon-12. Some of it, there are some isotopes of carbon that are higher than carbon-12, but since it's so close to 12, this is telling you most of the carbon that you see out in the world is carbon-12. Okay, so this is a weighted average. So the average atomic mass represents the average mass of the isotopes that compose the element, weighted according to the natural abundance of each isotope. So, like this one. You see that this is not a whole number. We talked about last time that this is the atomic mass, which is not a whole number. When we talk about mass number, that's a whole number. But atomic mass or average mass, that is not. And in order to calculate this atomic mass, right, this weighted average, you're going to need a few pieces of information. So the first one is that you're going to need the percent abundance of each isotopes, and you're going to use them as a decimal. Typically, they'll tell you them like as a percent, right, maybe 89%. So you're going to use this as 0.89 in your calculations. And then you're going to need the mass of each isotope of that element. And then the way that you're going to calculate it is it's going to be average mass, right? So this is what you're trying to solve for. So the mass times the percent as a decimal, right? This one as a decimal. And then the mass times the percent is as many isotopes as you have. Okay, so let's try this. Here's an example. So our problem is calculate the atomic mass of potassium if the abundance of the atomic mass of the isotopes making up its naturally occurring samples are as given below. So we have two different isotopes. We have potassium 39 and potassium 41. Okay, and so remember, those are the masses. So here are the actual masses. Their actual masses won't be whole numbers. They're going to be, you know, some kind of decimal number. This, you know, gets rounded. That's how we're getting this. This is always going to be a whole number. This is a mass number, but in reality, they have not whole numbers. So we needed their atomic masses and the percent abundance. And again, remember, we're going to use those percent abundances as decimals. So the way we calculate this, right, so we have in our formula from before, we have our average mass equals the first one, the mass times the percent abundance, plus the mass times the percent abundance. And again, make sure those percents are as decimals. And we're going to follow the rules for multiplication division, right? Remember, we are always going to follow sig fig rules. Since I've taught you your sig fig rules, from here on out, you must follow them. If at any point you break your sig fig rules, know that you may lose points on whatever you're turning in, okay? So first, we'll do our multiplication division, right? We'll multiply 38.964 times 0.9312, and that gets us 36.28. Since there are 4 sig figs here and 5 sig figs here, that means our answer must have 4, right? Because our multiplication division is the fewest number of total sig figs. And then for this one, 40.962 times 0.0688. So there are 5 sig figs here and only 3 here. So this is wrong. This should be 2.82 for 3 sig figs. My apologies. Yeah, so multiplication division rules. So then after you get these numbers, so this is, I'll write this cleaner, 36.28 plus 2.82, okay? And then you'll follow the sig fig rules for addition subtraction. And addition subtraction is numbers past the decimal point. So this has 2 numbers past the decimal point. This has 2 numbers past the decimal point. So our answer must have 2 numbers past the decimal point, okay? And then always include your units. So our units here are AMU because that's what we are using up here. AMU stands for atomic mass unit. And it's just what we use. It's kind of like grams, except really, really small. It's the mass of the atom instead of, you know, the mass of a mole of our atoms. So to get some practice with these, you're going to work independently on the Chapter 2 lecture worksheet, problems number 1 through 3. So these are going to be the problems below their tables. Last time you could have done that first table. Actually, I think you could have done both of the 2 tables. But now go ahead and do problems 1 through 3. Give yourself 10 to 15 minutes, so pause here and then come back. I have given you 2 hints. Number 1 is really straightforward. Number 2, your hint is that what should all of your percentages add up to, right? And that should help you figure out how to solve number 2. It's a little bit tricky, but some of you should be able to get it. Number 3 is tough. That one's a tough one. You're going to kind of have to solve it as a system of equations, like you learn in math class. So can you write 2 different equations, and then can you solve the system of 2 equations? That would be more your challenge problem. So go ahead and pause here, work on those problems, and then come back, and I will show you how to do them. Answers. So this is the first one. Magnesium has 3 naturally occurring isotopes, and it gives you the 3 isotopes. So magnesium 24, so this is the mass of this isotope, but we have an actual mass here. So this is our mass that we're going to use. This up here, this 24, that's just the mass number. And then we also have magnesium 25 and magnesium 26. So since for all of these we have the mass and the percent abundance, we can just plug it into that equation that we had on the last slide, which was the mass, right? Our average mass is going to equal the mass of each isotope times its percent abundance as a decimal. And we'll just keep doing that for as many isotopes as we have, right? So here we're going to have our mass is equal to our mass of our first isotope times its percent abundance as a decimal plus the mass of our second isotope times its percent abundance plus, and I'm just going to continue this on the next line, the mass of that isotope times its percent abundance. So we can go ahead and multiply those all together. Make sure you're paying attention to sig figs though, right? So this has 6 significant figures, this has 4. So when we multiply those together, our answer for that is going to have 4 significant figures. Same with these, right? And for these. So all of these, after we multiply them, we'll have 4 significant figures, which means when we multiply those out, we're going to get 18.95 plus 2.499 plus 2.861. And then we're going to follow the numbers past the decimal rule, right, for addition subtraction. So this has 2, this has 3, this has 3. So our answer can only have 2 digits past the decimal, which means this is going to be 24.31 AMU. Okay. All right, so that is how we do this first one. The next one is a little bit trickier, but still fairly straightforward. We have our 2 isotopes, bromine 79 and bromine 81, and this mass here, this is our average. That's like where we put mass equals, right? That's our average there. It gives us the mass of bromine 81 and its abundance, but it wants to know stuff about bromine 79. Okay. So here, if we were thinking about this, right, we have our average mass, which is 79.904, and we don't know the mass of bromine 79, so I'm just going to write M, and we don't know its percent abundance, but we know stuff about bromine 81. We know its mass, 80.9163, and its percent abundance. So my hint that I gave you was that what do all of the percents add up to? And all of the percents will add up to 100. So if we know that one of them is 49.31, we can do 100 minus 49.31, and we'll get that the percent abundance of the other one is 50.69%. So we can actually plug that in here, and we can solve for the mass of bromine 79. So we can go 79.904 is equal to, right, we don't know M, but now we know this, and I'll just carry the rest of it down from above. Okay, so now we know all of that, so we can go ahead and, solve for M. So again, this has 6 sig figs, this has 4, so when we multiply those together, we'll get 4 sig figs. So we have 79.904, and we get 0.5069 M plus 39.90. Okay, so now we're going to subtract 39.90 from both sides, and I'm writing it out like this to show you that we need to follow the addition subtraction rule over on the left. We have 3 numbers past the decimal and 2 numbers past the decimal, so our answer must have 2 numbers past the decimal point. So we're going to get 40.00 is equal to 0.5069 M, and then we're going to follow the multiplication division rule, which is fine because this has 4, this has 4, so our answer, when we divide both sides by 0.5069, is going to have 4 sig figs, so we're going to get that our mass is going to equal 78.91 AMUs. And the goal of this problem was to figure out the mass of bromine 79 and its percent abundance. So we have 2 different answers that are happening for this. So a little bit trickier, but still pretty manageable. The next one is quite a bit trickier, and my hint to you was, can you write 2 different equations and solve this as a system of equations? most people can solve for the first one. So we have this average mass that's here, and it gave us the masses of both of the isotopes, but we don't know the percent abundance of either one. So if we were to write this out, we can say, okay, 35.4527 is equal to, we have the mass of chlorine 35, 9689, sorry about that. And so that would be, let's say that one's X, okay? And we have the mass of chlorine 37, 36.9659, and we'll call that Y, just because I told you we're going to solve a system of equations, right? So we don't know anything about X, we don't know anything about Y, except if you think about what I told you on that last problem, we know that X and Y, those percents, should add up to 100, right? So we can think about like X plus Y equals 100%, but we want them as a decimal, right? So if we think about 100 as a decimal, we have X plus Y equals 1.00, and I'm going to include a couple more zeros just for good measure, because we don't want to be limited here by these significant figures, because it's going to add up to exactly 100%. We want to be limited by the significant figures of these masses up there. So they all have 6 significant figures, so I made my 100 have 6 significant figures as well. Okay, so now thinking about this, we can rearrange this second equation here, this X plus Y equals 100%, and then we can plug it in to the initial equation. So let's say I'm going to solve for Y. So I'm going to, subtract X from both sides, and I'm going to get that Y equals 1.00000 minus X. So now I can take this, and I can plug this in for Y, and then we're going to have an equation that only has one variable in it instead of 2. So we can write 35.4527 equals 34.9689x plus 36.9659 times 1.00000 minus x. Okay, and I can distribute this in now. So we get 35.4527 equals 34.9689x plus 36.9659 minus 36.9659x. So then you can go through and just, solve this like you would any other system of equations, right? You can, add that 36.9659 to both sides. You can subtract 36.9659 from both sides here. Sorry, that's a subtraction. And then you can combine those x terms, right? You can combine this 34.9689 and that negative 36.9659. And eventually, rearranging, solving for that, we are going to get that x is equal to 0.75774, which means that x is equal to 75.774%. Okay, and again, that was the percent abundance of chlorine 35. Okay, so now in order to finish answering the question, we need to figure out the percent abundance of chlorine 37. So we can just take, our 100%. We can subtract out, another 0, there we go. Subtract out 75.774. And we can get that our percent abundance is 24.226%. And again, that one's for chlorine 37. So this one was a little bit trickier, but still pretty manageable. The key for this one was writing this equation. Because once you have that equation, then you can rearrange, right, and solve for y, or you could have solved for x. It would have worked out just the same. But that was the key, is knowing that the percent abundances needed to add up to 100. So that's when I was talking about those system of equations. This would be our first equation, and this would be our second equation. So if we have 2 equations and 2 variables, we can solve it. Okay, on to a little bit about the periodic table. There were a lot of people that worked on the periodic table. They came up with the law of triads, which grouped elements in groups of 3. They came up with the law of octaves, which said that, after every 8 elements, there was a repeating pattern of properties. And all of these were, work that kind of led up to the development of the periodic table. And it's not overly important for this class, but if you're really interested, you can go check it out, or you can email me and I can send you some other slides that are on that. But all of that was just working on trying to figure out a way to organize the elements. They didn't have all of the elements at that time. They had, some of them, and they essentially started grouping them together by, okay, these ones have similar properties, like maybe all the alkali metals, right? They all react with water. Or, all of the halogens have similar properties, right? And they were able to group them. And then people started trying to put them in order and see these recurring patterns. But DMITRI MENDELEEV is the guy that I really want you to know. In 1869, he published a table of elements that organized the elements by increasing atomic mass. This guy, DMITRI MENDELEEV, he is known as the father of the modern periodic table. He essentially gets all the credit with organizing the elements in the way that we have them on the periodic table now. And his work on organizing them wasn't all that revolutionary, except for the fact, he took this thing, a periodic law, and then he applied it. Okay, so we'll talk about periodic law, and then I'll show you why his periodic table was so revolutionary. But periodic law says that if you put elements in order of increasing mass, certain sets of properties reoccur periodically. So like lithium, sodium, and potassium, those are all water reactive. Those are all alkali metals, and they happen every 8 elements. And then, like beryllium and magnesium and calcium all have similar properties, and they happen every 8 elements. And so he said, okay, there's this thing that happens. Every 8 elements, we have a recurring pattern. So he said, okay, well, what if instead of putting them in a line, we stacked them up? So these are ones that were known at the time. And so he arranged them so that elements with similar properties fall in the same vertical columns. So all of the alkali metals have similar properties, all of these alkaline earth metals, the halogens, the noble gases, right? So elements with similar properties fall into these columns. And so that was really cool, right? No longer did we have them in a line, we now have them in a sort of table. And we were able to see more information about the elements because now they're arranged in order of increasing mass going left to right, and by similar properties going up and down. So that was super cool. But one of the reasons that he gets all of the credit is because he laid out his table like this, okay? And so the key part here is that he left holes, okay? That is why he gets all the credit, is because of these holes. And the holes may not seem overly exciting to you, but they are. He arranged these elements in order of increasing atomic mass, and he left vacant spaces where unknown elements should fit. And so if we didn't know that they existed, right, how did he know to leave spaces for them? Well, he said, okay, I have organized the elements left to right in order of increasing atomic mass, and I stacked them up and down based on their properties. Okay, so when I'm thinking about this, going left to right, okay, so going left to right, in this period 5, there's an element here with this particular mass that has this property, and it has to go between these 2 elements. This element, there must be something there because it's going to have similar properties to yttrium, but its mass will fall between calcium and titanium. Similarly here, right, over in these spaces, he said, okay, there should be something with a mass that goes between here because it's got to react like these elements. Okay, so he left these spaces. And this is what's really revolutionary. And he said that if an atomic weight of an element caused it to be placed in the wrong group, so if an atomic weight of an element caused it to be placed in the wrong group, going up and down, then the weight must be wrong. He was so confident in his periodic table that he said, okay, if an element is in the wrong place on my periodic table that I made, then whoever did the mass of that element, totally wrong. They need to go back and fix it. And he was right. He went through and corrected the atomic masses of beryllium, indium, and uranium, which is super cool. And he was so confident in his table that he used it to predict physical properties of 3 elements that were yet unknown. So he's like, hey, this element here, I know approximately what mass it's going to have because it's going to have a mass between calcium and titanium. And I know it's going to behave like yttrium because it's in the same property. So he was like, we haven't found this element yet, but it's going to have this mass, it's going to react just like this, and he could tell you all about these elements, and nobody even knew they existed yet. And he was right. After people finally found these elements, scandium, gallium, and germanium, what he said about them, right, his masses and his reactivity were really, really close to the actual values. And people were like, whoa, that is so cool, right? How did he know, what these were going to be like? And it's because he came up with this really awesome periodic table, right? And so he is known as the father of the modern periodic table because he left those spaces. Those spaces were revolutionary, and because his table was able to predict the properties of those elements with nobody knowing anything about them, people are like, dude, he's got to be right. He's made this magic table, which is cool. However, wasn't all roses. In spite of all of these achievements, problems arose when new elements were discovered and more accurate atomic weights were determined. They had, these weights that we had before were more kind of like ish. And as we got better and better atomic masses, some of them started being out of order, which is a problem. So if you go find a periodic table, and you can pause this while you go find one, look at the masses of argon and potassium and the masses of cobalt and nickel, right? And these other ones. Look at the masses on our current periodic table. And if you'll look, potassium actually has a lower mass than argon. And, nickel has a lower mass than cobalt. But I just told you that Mendeleev's periodic table was in order of increasing atomic mass, right? So argon and potassium should be switched. But that wouldn't make any sense, right? Because we know argon is a noble gas. It has to go in this column. It behaves just like helium, neon, krypton, xenon, and our new element down there. So it has to go in this in this column, right? And potassium is an alkali metal. It reacts just like all of these guys. It has to go in that column, but their masses should be switched, right? So then it's like, well, maybe Mendeleev wasn't right. Maybe all of this happened on accident. So they're like, now what? Well, this guy that essentially nobody, I have a degree in chemistry and I really hadn't heard of him until I started teaching it. But this guy named Henry Moseley, he actually fixed Mendeleev's periodic table. He did this work with X-rays and he determined the actual nuclear charge. And the nuclear charge, anytime you hear we talk about that, that's just talking about the number of protons, right? It's the charge of the nucleus. Nucleus is positively charged. And so that's talking about the number of protons or the atomic number. But he figured out the actual nuclear charge of the elements, how many protons are in those atoms. And he arranged the elements in order of increasing atomic number. And that fixed everything. So the periodic table, the one we have right now, is not in order of increasing atomic mass. It is in order of increasing atomic number, or the number of protons. Okay, so he actually fixed Mendeleev's periodic table. And like I said, I've never heard of him. And Mendeleev is the one that gets all the credit. But this guy, Henry Moseley, he's actually the one that went through and fixed it. And if you'll notice, just kind of a random side note, the years here, okay, he actually did not live very long. He was killed during World War I, which is unfortunate because he was going to be, it looks like anyways, a really revolutionary scientist, but sadly he went to war and didn't make it back. So, crazy. Anyways, that is the end of this lecture on the periodic table. And so I will see you all next time when we do Chapter 2, Part 3. As always, send me any questions you have, and see you later.